So hey everybody, welcome to ARE Live. I'm Mark Tier, the founder of Black Spectacles. And today we're going to be covering project planning and design. You guys know the best way to prepare for these tests is to get as many questions under your belt as possible. So we designed our podcast here with that in mind. Today we have a mock exam focused on this one division of the ARE. And then the idea is that you'll have some concepts like this kind of under your belt. Some good news on the Prometric front that I wanted to share with you guys. Prometric is the company who actually administers the test. As you guys may know, so this is 2020, June 18th. Going back to March, Prometric did close their testing centers. The good news, there's a couple good news. Number one, they've opened back up. And number two, they actually, one of the designations they had made for their reopening was that some of the testing centers were only open for essential only exams, which of course begs the question, well, what's an essential exam? And the answer is that it turns out the ARE is an essential exam. So as of June 9th, they deemed all of the ARE tests as essential. So the good news here I'm trying to say is you can now take your test. And one of the things to keep in mind though is that they were opening up in some places only at 50% capacity. Now it varies from location to location, but since they're opening at 50% capacity, that means there's not as many seats available. So just want to encourage all of you guys to sign up as soon as possible so that you can get the ARE under your belt. One last thing for you guys, today we'll have a special discount on Black Spectacles individual memberships. And so if you stay tuned to the end of this, you'll hear about that. Our next section for ARE Live will be on July 16th. We're going to cover a programming and analysis mock exam with Mike Newman. PA is one of the mega tests, but we're going to cover the most important topics with another mock exam to get some extra practice in. So you can go to blackspectacles.com/podcast to register for that. And then a couple of updates to our products. For those of you who know, for those of you who are joining us for the first time, Black Spectacles is the first ever NCARB approved test prep provider for all 6 ARE 5.0 divisions. We offer 4 plan levels and durations, so there's a lot of flexibility there for which one you want to use. Our newest membership tier is called Expert, and that includes everything from our pro membership. So that means all the videos and practice exams and flashcards. But the new thing is that we've added virtual workshops. And so virtual workshops are every Sunday for 2 hours. They are workshops that are curated to focus on the topics that candidates struggle with the most. So imagine the hardest things on each test. That's what we cover in the virtual workshops. And what's cool is that we have a lesson that you do, kind of during that time, and then you and the group actually get feedback from a licensed architect, followed by some Q&A. So there's lots of it's a great opportunity to kind of fill in any of the blanks or get any extra support you might need to add on to your Black Spectacles membership. Our updated firm memberships do include these virtual workshops. So if you and your colleagues want to benefit from virtual workshops, just fill out the form at blackspectacles.com/firms, and we'll reach out and get you some more information about that. And in fact, we just dropped a link in the chat box to make that easy. We're going to be engaging exclusively in our ARE community today. So if you're sitting in front of your computer right now, go to your browser, type in community.blackspectacles.com. And then if you go to ARE Live, you'll see that pinned to the top there is today's mock exam for project planning and design. And what we're going to do is, if you have any questions, instead of using GoToWebinar, put your question in there. And myself and a couple of other people are tuned in, and we're all going to make sure you get your answers. And one of the things that comes along with that is everyone who posts in that thread on community.blackspectacles.com will be eligible to win a free Black Spectacles t-shirt at the end of today's podcast. So stay tuned for that. My guest today is Mike Newman. If you don't know our guest, he is a senior lecturer at the School of the Art Institute of Chicago, as well as the founder of Shed Studio, and he is the instructor for Black Spectacles online ARE exam prep lectures. So thanks for joining me and our group today, Mike. I'll let you take it from here.
All right. Today we're talking about project planning and design. So this is that time period on the sort of scale of a project where you've already done all the programming with the client and you've already done all the sort of preliminary analysis, and now you're trying to sort of take that and turn it into a design. And so you're moving from analysis into actual design work. Now they pretty carefully try to stay away from the terms on the exam: schematic design and design development and contract documents, in terms of how the tests relate to those. But essentially, this is somewhere between schematic design and design development. And then as you get into moving from design development into contract documents, that's when you'll get to the next one, which is really talking about documentation and all of that, where you're getting into not just that it's a steel beam, but how big a steel beam it is and all of that. But in this stage, we're talking about that schematic design, design development kind of range of a project. So let's just jump in. We have a couple of different examples of questions, and these are just meant to sort of tease out some issues and ways of thinking about things. Nothing sacred about these 5 questions, just trying to give you a sense of the sort of type of questions you might get, and a chance to sort of think through how you would approach them. So let's jump in. Number 1. While working on the design for a new 3-story office building, it falls to you to figure out how large the stairwell will be. From the building code, we know that the minimum path width is 48 inches. Some situations it'll be 44 inches, some situations it'll be more. It'll depend on the occupancy of each of the different levels of the building. So we just have said, okay, it's 48 inches. From the preliminary design, we know that there is a floor to ceiling height of 9 feet and interstitial space for mechanical lighting and sprinkler pipes of 36 inches and a steel structure system, including the slab, of 22 inches. How big is the footprint of the switchback stairwell? So the thinking here is that it's sort of expecting you to sort of understand what all of those different pieces are, and kind of that it sort of logically makes sense as you start to sort of piece these things all together. So just as a quick sketch here, if I've got a person, that's a very tall person apparently, 9 foot from floor to ceiling, and then we've got space above that that's, what was it, 36 inches, so 3 foot. And that space is for all the ductwork, light fixtures, pipes with sprinkler heads on them, all of that kind of stuff. And then above that, we've got a little slab with, I don't know, some sort of steel. I'm just drawing it like it's an open web just because it's easy to recognize. Got our structure up there, and then presumably there's another floor up here with somebody else standing up there. And so when we're thinking about the stair, the floor to ceiling is an interesting number, but it's not the number we care about. What we really care about is the overall dimension of floor to floor. It's sort of an obvious point, but it's one of those things that it is super easy in the middle of one of these exams. You're moving fast, you see that 9 foot, and you're like, okay, that's the number I need. And you got to make sure that you're actually using the correct number. So we add all that up. What this last one was, what, 22 inches, I think? And I believe that ends up being 166 inches. So we got 166 inches total from floor to floor. Now, what we're trying to figure out is how big our overall stairwell is. What's the overall footprint of that stairwell? And you can note that when you look at the answers, it's not super specific. It's saying a minimum of. And so it's sort of implying that there's a little bit of flexibility and how you're going to answer this. But let's try to figure this out. All right, so we got 166 inches from floor to floor. Therefore, what are we going to do? Well, we want to figure out how many risers there are in order to then figure out how many treads there are. So first thing we're going to do is we're going to take 166 and we're going to divide that by 7. So 166 divided by 7 is going to be, what is that, 23.71. Well, we can't have 0.71 risers. That would be a tremendous trip hazard. So obviously what we need to do is round. Now, it's easy to forget and you round down to 23. That would be a mistake because that would then put each individual riser slightly larger than 7 inches, and 7 inches, a 7-11, 7-inch riser, 11-inch tread is the sort of standard minimum numbers for an accessible public stair. And so if we rounded down to 23, that means each of those risers would be 7.1 or something like that. It'd be higher than 7, so that's no good. So we have to round it up to 24, which means we have 24 risers. Now, in fact, we actually don't really need to know the riser height to answer this question, but just for fun, if we then said 166 divided by 24, we're going to get 6.916, something like that. So each riser would be a little bit less than 7 inches, just slightly less than 7 inches. But the key thing we know is the 24. That's the key piece of information that we're looking for here, because now we can actually figure out from the number of treads how we're going to make this work. So you can divide that in half. That's going to be 12 risers per side, because we've got, you know, risers on each side. And so if we have 12 on each side, that's going to add up to 24. And then the other thing that tells us is that we then have 11 treads. Right? If we have 12 risers, we have 11 treads because there's one on each end. So we have 11 treads, but the other thing we know is that the space on the side of the actual floor area, so where there's a door, we need to have a little bit of extra space in order for that door to work. So conceptually, we just sort of think of that as another tread, even though it's on the face of the landing. So if we think of that just for our quick addition purposes, we can think of that as 12 treads. And then the question becomes, well, how big is the landing? Well, if it's 48 inches across in each of the travel depths, that means it's going to be 48 there as well. And then in this case, I'm going to say it's 48 from our sort of imaginary line of that extra 12th tread, which is actually on that landing. So we've got 48 plus 48 plus 12 times 11, which is 11 inches, which is that minimum size of a tread in a public stair. And when we sort of add all that out, that's going to get us to 19 feet. Now, I just took a very long way to get to that. You could actually answer this pretty fast because a lot of this is pretty sort of, you can kind of generalize and get reasonably close. You don't need to do all of the calculations. I was just doing it so it would be clear. So we have 19 feet as our main length. When we take a look along, that gets us to B. There's 0 chance on any regular size stair you're going to get a switchback stair to fit in 12 feet. 26 feet if you have a very large floor to floor, or if you're trying to do something else on the landing, then maybe you'd get as big as that. But 19, 20, 22 feet, that's a very typical range for a switchback stair. Now, note that it didn't say anything about areas of refuge. It's possible in certain situations you'd need to add space for that, but it didn't ask us about that, and it didn't give us any specifics of code information for us to worry about that. So the answer in this case would be the 19 by 9. You could actually do it slightly less than the 9 foot, but you do need about 8'8" at least, so 19 by 9 seems like a pretty good answer. All right, moving on.
Nicely
Question
done.
number 2. All right, your client has said they want to use natural systems to the extent possible. Preparing for a schematic design, you have been asked to start the conversation about the landscape design. On the site plan shown for the house renovation in Kentucky, place the tree to help provide shade for the house. And we have a couple of different locations. So this kind of question, this is a pretty simplistic version, just to kind of get the idea across. But this kind of question would actually most likely be the other kind of question type, where it would be a drag and drop, where you would be able to grab, in this case, the tree. In other situations, it might be the vapor barrier, and you're going to put it into a wall section. It might be the solar panels, and you're going to put them on top of the roof plan, or something where you can grab some part of the drawing and then place it onto the site. And then on the site, there'd be some pretty generous idea of, like, if you got it reasonably close, that they would assume that you were going for the right spot. You know, they're trying hard not to let just the peculiarities of the specifics of your using a mouse and, you know, all of that to move a piece, that, you know, you don't have to get it in exactly the right spot. They would give you a little bit of range, but the idea would be that you would understand the sort of question well enough that you could place it directly onto the site. In this case, because we're doing this in this sort of unusual way, we don't have that technology available on this version. So we're just asking, okay, there's a couple of letters in there, which one corresponds to the best answer? So we've got A right there, we got B right in that spot, we got C up over there in the corner, and we got D up in the other corner. First thing we can say is, we know since north is up, there's a north arrow over there. Since north is up, we know that C and D are not going to be particularly helpful. The sun in Kentucky and all of the United States is going to rise in the east. That's what my mom used to always say, was when I was trying to figure this out when I was a kid. She'd say, it rises in the, it's like bread, it rises in the east and it sets in the west. I understand that's a ridiculous, corny thing to say, but it's how I've always remembered it. And so the sun rises in the east, so the sun is rising somewhere in this direction, and it's setting somewhere in the west, which is that direction. In the summertime, that direction, the rise will actually be just slightly north of east. And in the winter time, it'll be pretty significantly south of east. And then the same thing would be true over here, south of west for the winter and just slightly north of west for the summer. So that's where it's rising and then setting, but it's going mostly to the south. So the sort of arc of the sun is doing that, which means that if the sun is, say, over here, a tree at D is going to put a shade area nowhere near the house. It's not going to help us any. If the sun is over there, that sun shade area is also still not going to help us any. And certainly if it's up at the center line of the arc, it's not going to help us any. It's going to be just going onto the sidewalk. So we know C and D are definitely not it. So then the question becomes, is it B or A? And I would not be surprised if quite a few people put B as the logical spot, which seems reasonable, because if we know that the sort of sun at its majority of the time is to the south of this structure, then it seems reasonable that we would want to put the tree that we're going to use for shading to the south. But in actuality, that's not wildly helpful to us. If you think about it for a second, when do you want your tree to give you shade? Do you want it in the winter? No, you want it in the summer, right? That's the time when having a shade is going to be important. So in the summertime, that sun is going to be on a very high angle. And so it's coming down and it's causing shade pretty much just below where the tree is. So in this case, at the time when you really want it, you're going to get a little bit of shade, maybe onto the deck, but essentially it's not going to be terribly useful to you. The correct answer here is going to be in that A location, because at that spot, because the sun has just started rising up on the east side, it hasn't gotten to its full potential height yet. That means I'm going to get, as the sun is over in this area of that arc, I'm going to get shade that's doing that. And I'll get it both in the winter and the summer, but the one I really care about, obviously, is the summer. So C and D, not even going to give any shade on the house. B gives a little tiny bit of shade onto the deck in the summertime, but A will actually function. This is one of those ones they like to ask questions like this because, like I said, the immediate thing you think of is, well, the south side, that's the one that you deal with the sun on all the time. But in fact, actually, it's in this case, something like a tree, which has height, but with that tall angle of that summertime, noontime sun, you're essentially putting a shade right below it. And so you just have to kind of be able, when you see a plan like this, imagine it in 3D and then think about those sun angles, and you should be able to answer it very, very quickly and easily. Right off the bat, you would have just gotten rid of C and D because you know that on the north side that's not going to be helpful. So then it would really be only about A and B. Now, interestingly, if this had been a drag and drop, A would have been one of the places you could have put it, but then the other place you could have put it would have been over here, which would have had the same issue, that low angle. You would have been able to get shade over there as well. So the answer, if it was a drag and drop, would have allowed both of those possible answers.
The question here is, they observed that Kentucky was mentioned in this specific question. And so the question was, are you expected to know the location of cities? What if a person is not too familiar with the geography of the United States? I wonder, Mike, what you think about that question about Kentucky.
Yeah, that's a great question. I believe that they would ask. I believe they would ask questions in a more like a temperate city, or something where it gives you the information you need, or a hot, humid city or something. They would give you the information you need in there. It is not expected that you would know all of the locations of all the major cities. It's sort of a shorthand for, like, if you're talking about the north and cold cities, you might use Minneapolis, for example, because that sort of tells you that. But I think on the actual exam, it would say, in the northern city of Minneapolis or something. I could be wrong about that. They've changed that a little bit. I know years ago they did use cities, but then I believe they moved away from that because of this exact question. I don't think they moved back. So I believe they would always give you enough information, so no, you wouldn't need to do that. I just like giving it a specific place because it, first of all, tells us it's in the United States, in the main body of the United States. If I said Sao Paulo, then that would change everything dramatically. It would all flip, right? North would be south in terms of the the way the sun is going, and it would just change the whole conversation. If if it was something right on the equator, that would also be a little different. So just the fact that we're saying it's in the United States and it's sort of in that body that we can roughly judge where the sun is without having to really kind of think about it. But yeah, that's a great question. I'm almost sure that they would give you more information if that was meaningful.
Yeah, I think that was great. That was kind of what I was thinking as well.
Yeah, and like I said, I know years ago, like back when I took the exam back 25 years ago or whatever it was, they did actually use specific cities, but like I said, I'm pretty sure they don't do that anymore. All right, number 3. While finalizing the basic designs for the wall system of the 3-story office building, the project architect wants you to research the presumed wall thickness between tenants. Clearly, one concern is fire rating, right? Obviously, that's going to be a big concern. Is it a metal stud with a double layer of drywall on each side and it's a 2-hour wall? Is it a single layer drywall on each side and it's a 1-hour wall? That'll depend on your code analysis. Is it, what kind of separation do you need from different tenants? So clearly, one question is going to be about fire rating. But another concern is sound transmission from one tenant to another. When researching wall types, which of the following would you be looking into while considering that concern? So the interesting thing about sound is that it's a very unusual problem to deal with. With sound, the issues are essentially, without building a separate building, there will be sound transmission that goes from one side to the other. Sound travels through the air, but it also travels through structure and materials. It becomes vibrations when it's in materials, and then when that vibration gets to, say, from one side of a tenant wall to the other tenant side, then that vibration then becomes sound again in that space. And so it's almost impossible to really stop sound from transmitting from one side to the other. But there are certain things you can do, and sometimes they involve creating a thickness of wall. So instead of using, let's say, a 4-inch or 3.5-inch stud, 3 5/8-inch stud or something, if you use a 6-inch stud, it would have an impact on sound transmission. If you did 2 3.5-inch studs and just had them next to each other with a little gap, and then drywall on either side, that would make a difference. Putting sound attenuation blankets, which it looks like fiberglass insulation essentially, inside will make a difference. But all of those things they'll make a difference for different aspects of the sound, different hertz essentially of the sound. And so getting an idea about what is the important aspect between different tenants. If you have tenants that maybe are, say, a law office, and it's very important that you can't hear somebody through the wall because they don't want private lawyerly type conversations to be able to make it through a wall, then that's one thing. If it's a radio station, that's a very different thing, right? They need a very different level of sound control. So you would need to sort of to truly know what walls types to use. You would really need to do some research about the different wall types. Now, most of the time we don't worry about it that much because we just check the wall types and make sure that the sound transmission is okay. But the research that you would be doing, and we can see it pretty much straight off just from the way it's written, would be C, which is going to be the STC rating, and that's the sound transmission class. Note the transmission word there, right? That's the thing in that case that we're worried about, sound moving from one tenant to another. Now, there are many other sound issues that I would be worried about during this schematic and design development phase. I would also be worried about the internal sound. Like, just for a second, imagine for some design reason you decided to make the ceiling of this open office space glass. So you had this really hard and flat surface as a ceiling in that space. And then you had all these people in this open office, and they're all talking on the phone, or they're talking to each other, or they're clicking their keyboards, or they're doing whatever. Well, all that sound would go up and bounce off of that hard surface, and you'd get a huge cacophony of sound from that very bright surface. It would just bounce everything. That sounds sort of horrible to me as an office space. There may be other places where that's kind of cool, like when you're in the shower and you're singing, right? That hard surface gives you a lot of reverberation and makes you sound like a great singer, even though, like me, you probably aren't. And so there are places where that live sound is okay, but in an office space, it would just be overwhelming and it would drive everybody crazy. Well, that kind of question, that's not about sound transmitting from one side to another of an assembly. That's about reducing the noise inside the space as it's reverberating around, bouncing around in the space. And then that would be D, but that wasn't what the question was about. So if you think of like drop ceilings, they have NRCs that are set up in order to absorb a certain percentage of the sound. Now, it's not going to absorb 100% or anything like that, but it absorbs enough that it makes it so that the space becomes workable and livable, and you don't mind what's going on. You would be looking that up when you're trying to figure out some of the finishes, which would be pretty much around the same time, but the question was asking specifically about transmitting from one wall to another. So this is really an interesting thing to go look up. If you look up on any of the drywall companies, we'll have Georgia Pacific and USG and all those folks all have lots of diagrams online that you can check out. But you'll find that if I have, say, drywall and drywall with a stud in between, that will give me one thing. And you would think, well, what if I just added another stud and added another line of drywall and made the wall that thick? Is that the best choice? That seems like it would be a really good choice. As it turns out, weirdly, doing that, so 2 lines of studs with then drywall on the outsides and no middle stud, so nothing in that range, in that area, that is actually a better STC rating than the one that has the drywall in it. So it's a little weird. It takes a while to kind of get a feel for what's going on. The other thing to say about STC ratings is, like, you may have wondered about this when you've been, walking out on the on a sidewalk and you hear a car going by blasting music and you can hear the bass line, but you can't hear the rest of the music. That's because of the wavelength of the bass hertz. That wavelength is very big. It's very hard to contain it. It's relatively easy, sort of, to contain short wavelengths, which are high pitches, but those bass lines are really hard to contain. And so those big, long waves can kind of, this is sort of a little bit of a weird way to say it, but can kind of get captured inside these spaces, which is a useful thing. But there's really no way, just like in the way the car, when you hear the car going down the street, you can't block that bass line. There's really no way you're going to block a serious bass line from one tenant to another. But the thing you really care about is not so much that somebody could hear a beat of something going through. The thing you care about is people's voice. So the STC ratings are all set up about the different hertz range of a sort of reasonable range of human voices, because nobody really cares if you can hear something through the wall. The thing they don't want to be able to hear is actually specific language. So imagine your apartment and you have somebody in an apartment next door, and if they're on the phone and you can hear them talking their half of the conversation, it would be impossible for your brain to just shut that out. You would keep thinking, I wonder what her mom is responding with. You would just keep filling in the blanks, and it would drive you crazy. But if it's just a sort of low muffle, then it won't really bother you and your brain will just start to ignore it. So the STC ratings are all about human voice. So the fact that you have a high STC rating does not necessarily mean that you're stopping a huge amount of sound transmitting across. What it means is you're stopping as much as you can the sound that is really meaningful, which is the human voice. IIC, the impact isolation class, that's that sound. Like imagine a woman in high heels walking around in a loft building upstairs, and that hard sound, because it's a fair amount of load into one point, and so every step you hear that impact sound. Well, the IIC is about talking about assemblies and how they deal with the impact sounds. So if I'm trying to reduce that, I might be putting in neoprene layers below a wood floor or something to absorb a little bit of that impact. So understanding IIC, STC, and NRC for this exam would definitely be a smart thing to do, and really get a handle on how those things work.
I understand that a good sound absorptive wall will have bad STC.
I think if you're talking about like regular walls, that that can be the case, but there's a lot of wall choices out there, and it isn't necessarily true depending on all of the different parameters. You know, the vast majority of walls we do, just from a cost standpoint, has one line of studs. Like you start adding double studs and things like that, the cost per linear foot of that wall is going up pretty dramatically. So, you know, it's not something we do all the time. You'd only be that concerned about it in situations where there was a specific need from a design standpoint, like I said, a lawyer's office or something where they have, you know, very draconian issues. But there are definitely some situations in the simple walls where if you're using a system that absorbs sound easily, so it's good from an NRC standpoint, that can mean that it's allowing the sound into the wall easily, and then it's transmitting through, but not every time. Hopefully that makes sense. Okay, I'm going to move on. Number 4.
Okay, thanks, Mike.
While designing a new strip mall, and as I was about to say, I'm sure this is everybody's big desire for your career, is that you're really happy to be designing a strip mall. But okay, while designing a new strip mall for your developer client in temperate Chicago, kind of note that I put temperate in there just in case people didn't realize Chicago has both cold winters and hot summers, which is essentially what temperate means. You are trying to pick a logical HVAC system. Assuming the developer is concerned about first cost, which of the following would seem the most likely? So there's a couple of different sort of design issues that are being referenced here. One is the idea of first cost versus long-term costs. So first cost might be, you know, the example that is often given is for siding. Let's say you choose to use vinyl siding. You're putting vinyl siding up on the house, and that's great. And it lasts for 15, 20 years, something like that. And then you take a look back and you look at, well, how long would have we gone with brick, say, or with metal siding or something like that? Well, maybe the metal siding or the metal siding might last double that, 30 to 50 years. And the brick might last, as long as you're maintaining it, 80 to 100 years. And if you're maintaining it well, it could last significantly longer than that. So comparing those sidings, you would really need to say, well, if we have a 50-year time horizon here, and in that 50 years, I would need to put the vinyl siding up 3 times in order to be equal to a high quality metal panel. Well, then I only have to put the metal panel up once. Therefore, from a first cost, the vinyl is definitely cheaper, but from a long-term cost, then we have to add all of those times that I have to put it up once it starts to need to be maintained. And so I'm multiplying that by 3, and by that point, with that 50-year time horizon, then the metal panel probably makes more sense. And even the brick might make more sense, even though it's going to be much more costly. So kind of understanding what this sort of time horizon of the design, what it really is, will make a difference. Now, developers are kind of in an unusual spot. In a situation where you have a developer and they're doing something like a strip mall, typically their time horizon is relatively short. Now, they want to make a solid building that will be durable and all of that, and pleasing, and gets people to want to rent there and to put their stores there and all of that. But they don't have typically like a 50-year time horizon or 100-year or anything like that, because that's just not the nature of a strip mall. When the what would be a good example? Starbucks moves in, maybe they're there for 8 years or something, and then maybe they move out and somebody else moves in. When the dollar store moves in or whatever, like they're maybe there for, again, 8 years, 7 years, 3 years, 5 years, something like that. Whereas if you were doing, say, a university building, your time horizon might be 100 years or something, because they're going to likely hold on to that building for a very, very long time. And so it makes sense for them to see those big savings and advantages down the road if they use higher durability materials, or high first cost materials that have low day-to-day running costs. So understanding the time horizon makes a big difference here. So this is a developer, and assuming the developer is mostly concerned about that first cost, and we're talking about HVAC systems. If we look at radiant flooring, that's just not, in this context, it's just not believable. The chances that you would put a very expensive radiant floor in and then the tenant would be gone in 2 years is just too high, and you would have to then rearrange the radiant floor. You have to dig up the concrete. It just doesn't make any sense. So even though I personally love radiant floors, they're by far the best way to do heating in a building. It's just not going to work in this context. It's too flexible. The other thing is, unless you have a very sophisticated HVAC air system that really is focused on the humidity level in the air, you can't really use radiant flooring for cooling. Now, you can, it's just that in reality, sort of everyday kind of reality, if you do that, what's going to happen is you're going to get a little bit of condensation on the floor. And in a place like a retail spot where you have public coming in and out all the time, somebody sooner or later is going to slip on that condensation. And so you just never would use that on a floor in a commercial setting for cooling. So radiant flooring is out. A trom wall is a very interesting setup. A trom wall, if you don't know it, is when I have a sheet of glass, and then just behind that glass, I've got some very intense material like concrete or masonry or something along those lines. And it's just a few inches, maybe it's 5 inches or something apart from each other. And the idea is that as that sunlight comes down, the sun comes in, penetrates through the glass, and then gets absorbed into that masonry. And so the masonry becomes a giant heat sink. It's a fantastic system. You can also add to it by doing things by putting little, the ability to put vents in at the top and the bottom. And then that way I can do things like have open the bottom vent and air can come up and then come through and bring in hot air. I can open the top outside vent and get rid of hot air. It's a really amazing and simple system. And the reason that nobody ever uses it, in terms of, I mean, people do use it, but hardly anybody uses it, is because it just drives everybody crazy that you put this giant sheet of glass 5 inches away from a concrete wall. And it just seems insane to people. But it's a really great system for certain parts of the country. Depends on temperate, it's sort of workable, definitely in some other spaces. So it's a really interesting idea, but definitely not something you're going to do in this context. I highly recommend. It's a good passive system. It's likely you could get a question on something like that trom wall or other similar passive systems. It's worth kind of having a basic idea of how those work. So then it really comes down to A or B, which is the commercial rooftop HVAC units or the central chiller unit. And both of these are plausible. All four of them are plausible, but both of these are certainly plausible. But the answer is definitely going to be A, the rooftop unit. And the reason for that is the rooftop units, they have a fairly short timeline. If you imagine, where would you want to be if you were in Chicago? If you were an HVAC unit, would you want to be sitting up on the roof in Chicago, or would you like to be in a nice, controlled basement space? Well, the chiller is likely to be in that nice controlled basement space. That rooftop unit is going to be in the sleet, the snow, the hot sun, the UV rays. It's going to have all of those troubles, but it's a off-the-shelf piece. It has everything included. So it's got the fan, it's got the condenser, it's got the supply, the mouth that goes out to the supply trunk. It's got the intake for the return, all as one box. And so you just literally go to a supplier and say, how big of a system you need, and they will order it for you, and it'll show up, and then you take a crane and you put it up on the roof, and you're essentially done. You just have to put some ductwork on the inside. And then when that dollar store goes out of business and a phone store moves in and you need to change the ductwork, it's a relatively easy thing to do. You're changing some simple ductwork, but the whole system can stay. Or if it's a big enough change, you just take that piece off the roof and get rid of it and put a whole new one on. Maybe you're doubling the size or something and you need a bigger unit. And because it's getting all that battery up on the roof, the expectation is that they'll only last so long. But that actually kind of fits to the scenario of a strip mall. The expectation is that people will be gone after a while, and the next person who comes in will install a new one, and it's appropriate for them. So in this particular context, A would definitely be the sort of most reasonable answer. Now, is it the most sustainable answer? Well, there's some ways that you could think of it as a sustainable answer, but probably not. Is it the sort of cheapest for the use and the need? Yeah, it actually works pretty well from a cost standpoint. So it makes a lot of sense. The central chiller, that's going to be sort of a classic university building or something. I've been in buildings where the chiller was from the mid 50s and it was still working great. So it's a totally different animal. You tend to use for whole buildings, whereas strip mall, you tend to want to have heating and cooling per each individual tenant. So it's just sort of understanding what is it they're doing, what's the design implication of these few words in this question. What does it tell me? So it tells me strip mall, that tells me individual tenants, that tells me fairly high turnover. First cost tells me we're worried about that low first cost. We're not trying to build a Cadillac system that's going to be there for 100 years. And so when you really start thinking about it through with those lenses on, A really becomes the sort of only logical answer.
Gianna asked the question, what is the most common application that you see trom walls used?
Yeah, the trom walls are used, you'll see them in a lot of houses where somebody is just really interested in that idea. It doesn't have to be concrete or masonry. You could have water, like big tubes of water can be used. There's a bunch of different ways that you can do the concept. But so you'll see them in houses and things like that, where that radiant wall radiating into the space, it actually has some real meaningful impact on the heating up in that interior space. Because the whole idea of the trom wall is that you're taking that hot sun during the day and you're delaying it inside that big heat sink. And then by the time that the heat gets all the way through that big heat sink onto the other side, it's now nighttime and it's now giving off that heat into the space. And so it's a way of delaying the natural solar gain from the sun. But if you're doing that on a wall where the room is 300 feet long, that wall is not going to be radiating 300 feet into the space. So it doesn't really make sense on very, very large uses, but houses, a lot of sort of institutional type buildings where there's smaller spaces, like maybe libraries and smaller university buildings, dorms and things like that. But like I said, it's not used a lot. Everybody thought it was going to take over, and like if you look at stuff from the 70s, when people kind of figured this out in in a really useful way, there's all these writings about how trauma walls were going to take over everything because they're so great, and then just people just couldn't stand the idea that you're looking through a piece of glass, not to a piece of concrete. It just seems so weird to everybody. The other problem is the windows get dirty, and so you have to make them so that they're operable, so you can clean them. And it's just weird to clean a window that you can't see through. You don't use for view. So it's an awkward thing. It's just they're super interesting, and the fact that when you start adding in those little vent spots at the top and the bottom, on the outside and on the inside, there's all sorts of convective currents you can get going that can give you cooling, they can give you heating, it's just a very flexible system that has this one downside of looking at the concrete. Okay, back to number 5. In the office building design,
Thanks, Mike.
It is determined that having a full supply duct system and return duct system at each floor will likely be too expensive. What would be a typical design change to reduce cost for this issue? So for an HVAC system, we have a big fan in a air, what we usually will call like a furnace, although it's an air handling unit in reality. So we have this big box with this fan in it. And that fan blows across a filter to sort of clean the air. It blows across a coil, and the coil has either hot liquid or cold liquid in it, depending on the season. And if it's blowing across the cold, then it's cooling the air as it goes across that coil. And it blows from there into the supply system, and it's blowing out into a trunk line that then branches out into the space. And the air is pushing through the trunk line, pushing out into the branches, and then eventually getting to a register, which is one of those open spots where it blows out into the space. So that's great. We're blowing this nice cooled or heated air out into our space. But we also then need to get that air and bring it back. Now, there's going to be an interesting post-COVID-19 reckoning about HVAC systems. There's a sort of a lot of talk about how maybe we don't want to return as much air as we have been. But up until now, most settings, some places you'll be doing a return of maybe 90% of the air. In some other settings, it might be more like 75 or 60% of the air. So I'm grabbing that air that we've just pushed in. It's as that supply air has gone into the space and it's flowed around you. And then, eventually we want it to get back into our return system that then is going to take it through branch lines, through a trunk line, back into the air handling unit. So it can then get blown across that fan again, go through the filter again, go across the coil again, be reconditioned and become supply air again. And typically, as I said, sort of pre-COVID, we would be adding some outside air into that mix. So if we're returning 80%, say, of the air return coming back from the space, we might be adding 20% of outside air in. And that outside air is going to keep fresh air coming into the space. It's going to keep everybody awake. You don't get that recycled air quality, all of that. As I said, in the sort of reckoning post-COVID, it may well be that we have a problem with that concept, and we may need to up it so that we're actually only returning, say, 50% or 40% or something, in order to make sure that we have a chance to clean more of the air and bring more outside air in as a way to kind of keep everybody safe. The reason that we don't do that anyway, the reason that for years we obviously we could be always using a lot of outside air, but the reason we don't do that is because, well, if it's winter and the outside air is 0 degrees or 5 degrees or something, that means bringing in a lot of very, very cold air. We now have to condition it way more, bring it up into a reasonable temperature in order for us to be able to use it. It's going to take a lot more energy. Same thing in the summer. Say it's 95 out. That means we're pulling that 95-degree air in. We've got to lower it way, way down in order to then make it useful. So from a sustainability standpoint, we want to reuse as much of the air as we can. From a health standpoint, we would love to have as much fresh outside air as possible. And so it's always a bit of a question back and forth. Now, the trick problem here is on this question is that what we're talking about is this 2 duct systems. So we need to get the supply air to all the places that we need to get it to. So generally that's going to be towards the perimeter of the building because that's where the problem is. It doesn't really make sense. There are certain situations where this can work, but most of the time you're going to be supplying air, cool air in the summer or warm air in the winter towards that perimeter wall. And if you think about it, if that's where the problem is, you're worried about losing heat or gaining heat through that perimeter wall, then you want to counteract that right where the battle is, which would be along the perimeter. It doesn't really help you a lot to dump a huge amount of conditioned air into the middle of the space, because that outside wall area is still going to be very cold or hot depending on the season. And so it means that we're going to be supplying that air all the way around the footprint, which means there's a lot of ductwork up in our ceiling. And if we then also need to have ductwork to pull all that return air back, well then, now we have 2 whole systems of ductwork which are competing with each other in terms of space. And if I have to have one cross the other, it's not really the end of the world if you have down at the very branch ends, those crossing each other. That happens all the time. But if I have trunk lines crossing each other, these trunk lines, even for a small building, might be 36 inches by 42 inches or something like that. They can be pretty darn big. And if I have to have 2 of those crossing each other, then I'm literally going to have to either lower the ceiling down to the point where people can't walk around, or I'm going to have to make the whole building taller, which obviously would be very expensive. So one of the ways that has sort of over the years been sort of figured out is just using the idea of the plenum system. So if we think about the section that we just looked at earlier, so there I've got my structure. Again, I'm just using the open web joist, so it looks like structure. I've got the ceiling here. I've got a space for ductwork, and maybe I've got outside wall here. I'm not going to get too into the details. So there I am sitting at my desk working. The concept of the plenum is I might supply all the way out here so that the air comes down right here by an outside window. So imagine that's a big window. And so therefore I'm dealing with the condensation on the window. The window is very bad from an insulating standpoint. So I'm putting the conditioned air right where the problem is to sort of battle it and become a buffer between me and that big window. The window is also going to be a radiant issue. So it's going to pull heat from me in the winter. So having that air become a buffer between me as a radiator and that window as a radiator, very useful. But if I have to have 2 full systems right here, it's going to get really hard to fit it all in. And so the concept here is, well, maybe somewhere way back over here somewhere, I've got my return system. And I can have a little opening in my ceiling there, and maybe I have another one here, and I have another one over here. And I just have up in that interstitial space an opening. So this is above the ceiling. That duct has openings into the space, that interstitial space above the ceiling and below the deck. right? So as the supply air is pushing out and it's pressurized and that air is coming out into the space and it's sort of blowing around me and it's blowing kind of by the window and it's kind of blowing all around, it's pressurizing outward. Well, if you imagine that all the way back to the air handling unit, as the air is pushed out, something needs to fill in the space behind it, and that's the return air. And so it creates a vacuum which is pulling the return air from that return system. So effectively, this return duct is sort of a negative space for the air. And so it's pulling air in. So air is wanting to go inward towards that return system up in that interstitial space. Well, what that means also then, if it's making that interstitial space a negative air space, well, then that's going to pull air through these holes, which don't look like holes, they look like registers, but it's going to pull air up from that space all over. And it's going to allow us to do this system without having to have a full second return system. We just have to have enough of it that we reach far enough around that the air can sort of find its way to it up in this interstitial space. So here at my desk, some of that air is also from the vacuum that's been created is going to enter up and sort of flow over and around the duct, maybe up into the space of the structure. It's just going to flow all around up in that interstitial space and find that negative need there, which is that return duct up in that space. And this is a classic way for office spaces especially. We don't usually use it so cleanly and simply in residential. There's a few places that have for various reasons, but institutional and office use this concept all the time. If you had to have this full system out here also by the windows, it would just be very complicated and all these ducts would be crossing each other. The fact that I can place this return system much deeper into the space and still get all of this air to flow all the way over to it means I can have a much smaller return system compared to the supply system. And so the sort of interesting thing here is this whole space that's got all the lights, it's got this other ductwork, it's got, you know, sprinkler pipes, it's got all that stuff in it. It's all becomes essentially kind of like a duct. And so it becomes the ductwork for that return system. It's not a duct, it's just the space below the slab above the ceiling. It's the interstitial space, but it works like a duct, allowing all of that air to find its way all the way over to it. Well, that interstitial space in this context, if you're talking about it from an air-based standpoint, that is a plenum. So B is the answer. Got the return system and use natural ventilation from windows. That's a totally reasonable answer for a portion. It's really not believable to have 100% fresh air supply. It's just not likely to happen. Maybe with the COVID thing, things will change, but I can't imagine it. Switch to a hydronic system, that's certainly possible, but it's a big change and it doesn't, as we said a minute ago, doesn't get us the air conditioning. So there's various trouble. And then D, I had switched to a basement chiller system, which needs no return system, but it does need a return system. That would be an incorrect statement. So it can't be D either. So by far the best answer here is plenum. And that's using that ceiling space above the ceiling to get that air back. Could we switch it around and use the plenum for supply? Yes, there's lots of examples of that. You don't usually do that at a ceiling, but it's possible. Sometimes you'll see supply plenums below a floor. You might have a raised floor and then you'd use the below that for pumping supply air in, and then it'll come up through the floor. Sometimes in theaters, you'll see it below a theater floor in order to get that cool air to sort of come right to where the people are. There's a bunch of times when you'll see plenums used in different ways, but if you see the word plenum this is the scenario that should really pop into your head. It's in an office space or kind of institutional space. There's a dropped ceiling. You're using that interstitial space as a air plenum.
All right. Well, thanks, Mike. I think that that brings us to a close. I think that's our last one there.
Yep.
Appreciate all the clarity there. So I want to thank you, Mike, for providing this mock exam and lecture, and thank everybody for tuning in. As I've mentioned in our next ARE Live podcast, we're going to review a programming and analysis mock exam with Mike Newman again. And we just posted a link to register in the chat box and go to webinar control panel, or you can just go to blackspectacles.com/podcast to sign up. To learn a little bit more about our ARE exam prep offerings, you can go to blackspectacles.com, where you can try out any of the course videos. And the lucky winner of a Black Spectacles t-shirt who posted in our ARE community during today's session is Brandon from Larson Architects. So Brandon, we're going to send you a note via email to get your size and shipping information. And just a reminder, if you'd like to be eligible to win a t-shirt for the next one, post a question about the mock exam in our community during our next ARE Live. And I should mention, obviously it's an open forum, it's a community, so it's a great place to get questions that you might have answered as you're going through and studying the material. We have these hotlines open up for each one of the different exams. And a hotline is a place where you can go. We actually have architects on staff who can answer your specific architectural questions. So if you run into any roadblocks, it's a great place to go on this ARE community to get your questions answered. For those of you who are ready to start preparing for the ARE right now, you can use coupon code PPD061820YT to get a 15% discount for the entire duration of your Black Spectacles ARE prep membership. And finally, tomorrow, we'll email you a follow-up about today's live broadcast. So please let us know what you think and share any suggestions that you may have. I promise we read every word that you write and use them to tune our next episodes. So thanks for watching.